Okay, so the topics that we are considering to be in the third module, which is the last module that we are about to do in this course here, is about electricity and magnetism, which from the past experience and everything, we never seem to get to the magnetism somehow. So bad. All right. But I hope it works in the sense that the way that I'm teaching is still based on the concepts of one is better than none. So it means if we go a little bit slower pace, but then you can pick up a lot of things along the way, it's better than just like, you know, brute force, try to get like, you know, push through everything and then so many topics that you cannot pick up at all. So I hope that this seems to be a good one. But I always have to report to the program saying that I cannot cover maybe the last two topics in the syllabus and all this stuff. But I hope you guys okay with those. All right. If you're not, then just let me know. All right. But Dan, I want more. I want, you know, I want everything. I want, you know, the whole stuff that you listed on the syllabus, and then you're supposed to go through all the topics. Then the pace that we go through is going to be a little bit different here. Okay. So what we are about to talk in this sort of like the first class in the module number 3 number 3 over here is about electric field. Here we go. And force. So now we have to deal with force again. That means we have to deal with vector one more time. You cannot avoid those anymore. So you have to come back and try to deal with vectors. Okay. And then we're going to have the concept of the field. This one is not new. You have done this a couple of times already in the past. However, it's going to be heavily used here because you are talking about something that you cannot touch it. Or, I mean, it might not even be real somehow. So you have to keep in mind that what we have here is like the fields. When you think about fields, is like, you know, Star Wars, like, you know, the force, the force, the dark force, or the good force, or whatever. The field is right here. And it's here in the sense that it might not be here, but it has some effects on things that you can measure, you can do experiment with. So physicists came with an idea of explaining those phenomena using the concept of field. All right. So I'll explain more about that. All right. And try to make an analogy to things that you have already familiar with, other kinds of fields. So what we're going to learn is what is the origin of those fields, and that has to be charges. Okay. And once you sort of like, okay, take that to be the origin of all the force and the fields, then we're going to learn how to deal with those electric fields. And once you get to that, the force will come naturally. And to explain all these things, actually, everything is based on this law right here. And now this is serious. This is a real law. It's a law of the universe now, as big as gravitational law. It's like sigma F equal to ma, or gmm over r squared, the one that you used in Newtonian physics. This is huge. We call it a Coulomb's law. This is the law that all of the charges in this universe has to follow. All right, this is the real stuff. Okay.
Okay.
Sounds like fun already. But just to be honest, guys, this is going to be the hardest part in the course. I don't know, maybe some of you will feel like thermodynamics will be the hardest, but in terms of the technicality, everything is here, guys. If this is going to be your last physics course in your life, I think this is going to be a grand finale for you, because you are going to deal with vectors. You're going to deal with calculus. Not only that, you're going to have the combined vector calculus into one. That's why we call it vector calculus. Anyway, so you will have a chance to deal with the calculus on the vector quantity. So that's going to be a lot of fun. All right. Just saying. Okay, guys. So I don't think we have to introduce much, because I think you have learned many scientific, you know, stuff, or you have already seen many things about nature composes of atoms, like, the tiny bits of stuff that build up everything in our universe. And if you think in terms of the molecules or atoms or other stuff, you can pretty much like decompose them into the nucleus. And you say, hey, it has a positive charge and have electrons orbiting around. You have to say, hey, that's a negatively charged, all those stuff. When you say those charge, this is it. This is the source of this additional force in our nature. All right. The one that you're familiar with the most, probably the gravitational force. And this is another force that comes hand in hand with those gravity. Yeah, you cannot avoid it. So think of this in this term here, guys. When you have mass that link to the gravity, you can use G for that, right? It's generate gravity. Here, you can think of charge to be as big as mass back in the gravitational story there. And that will lead to another kind of field, okay, of its own. And that we're going to say electric field. All right, you get an idea here? Okay, so now in our universe, all right, at least now we have mass. Any mass will pretty much have the gravitational pull. And then you can generate the interaction between those masses. They are pulling toward each other. Same thing with this charge. Any charge in this universe will generate electric fields. So when you have more than one charge nearby, they will interact. They can attract, but the complexity starts to come in. In the case of masses, they are only attract, right? Mass with mass, they attract each other. But in the case of charge, you have some complexity in the sense that there are two types of charges. Okay, one we name it positive, the other one we name it negative. So now the game is a little bit, a lot more fun in the sense that now you have an ability to not only attract, but you can also repel. You can push. You have a force that can be pushing between those charges as well. So you have, more stuff that you have to determine there. All right. But at least that is the sense that we're supposed to get to is charge is it's sort of like playing the same role as the mass that is playing in the gravitational force. Cool. Now, the additional stuff that shows here, you have two types of charge. And by Benjamin Franklin, maybe back in the history, he picked the one that accidentally take the negative sign to attach to something that seems like we are using the most. So I think you have learned about electrons, so many times in the past. And like electricity that runs in our household and everything mostly is responsible by electrons movement, right? And because at the time we didn't know that there is like a proton, there's electrons, anything. They say one type is negative, one type is the other type is positive. And later, when we found out that, hey, electron is the one that actually very mobile, it moves very easily. And it turns out it's coincide with the one that we already assigned a negative sign to it. So that's why we ended up with electrons have a negative charge. Cool? Okay, guys?
Okay.
It's just 50-50. All right. So if Benjamin Franklin decided to think the other way around, so we're going to have a nucleus, have a negatively proton, it's a proton we can negatively charge, and the electron will be positive. And our life will be a little bit better in the sense that we don't have to worry about the negative sign all the time. So too bad. All right. So it's 50-50. Okay. So that's what it is. So first thing first, take home message over here is there are two big classes of charge, either positive or negative. Cool. Now, on passing, it turns out this is a weird stuff. Even though it seems like, okay, Dan, that is fine. But there is another thing that I want to squeeze in here, even though we're not going to try to do anything sort of like quantum physics or anything. But this is the weird stuff if you think carefully. In our universe, it turns out charge is, we use the word quantized. I don't know if you're familiar with these words yet, but it's related to something quantum. You probably you have heard of like quantum computer or quantum computing, quantum encryption, all of those quantum stuff. So this word is attached to the things that come in lump or come in steps or come in a discrete format. So it means you're not going to have like a smooth value of this thing, but you come in like a step. a step. You have a jump. So that's why it turns out charge is quantized. What does it mean by quantized? Look at this. We have a fundamental constant over here. It's the electronic charge. So we have already found out that one electron will carry this much of charge, 1.6 approximately times 10 to the negative 19. The unit for that charge, we use Coulomb to honor Coulomb's law that we are about to, Coulomb's a physicist that started that Coulomb's law, all the stuff there. So electron, one single electron will carry with it 1.6 times 10 to the negative 19 Coulomb of charge. And it turns out this number is the lowest number that you're going to get for a single charge in our universe. Isn't that cool?
Okay.
ไม่มีใครตื่นเต้นกันได้นะ So it's like, hey, isn't that amazing? This is like a wow moment, guys. Okay, so this is like wow. It's like, oh my god, in this universe you cannot find any particle that carries charge of, let's say, 1.7 times 10 to the negative 19 Coulomb. No, that's not happen in this universe. All right, multiverse maybe, who knows, but not in our universe. Okay, so this is going to be the lowest number for any charge in our universe. It's going to be able to take. All right, for some of you that have heard of like a fractional charges, like the one that you break that crazy, you break away all those like nucleus and all this stuff into a fractional stuff. Don't worry about those yet, because those cannot be found in like a normal environment over here. All right, so let's talk about just the regular environments and everything. This is the lowest number, guys. This is the lowest number that you're going to get. Any other charges that you will experience will be the multiple of this number. Isn't that amazing? All right, just take my word for it then. All right, guys, so what you have over here is, well, Bajan, it's not surprising, because what you're looking at is negative 19. So the value of this one is so super duper small. So that means if you talk about 1 Coulomb of charge, that is a huge amount of electrons, and for us it's already smooth. It looks smooth, so it already looks continuous to us. But now, from the modern physics and everything, now we know it's a discrete. That's why we have a name. We sort of like say, hey, charge is actually quantized. Okay, cool. All right, next, what do they do? Once you have charge and now you have more than one charge around, it turns out they will interact. Okay, and because you have two kinds of charges, so that means if you have positive and positive charge nearby, this is what's going to happen. They're going to repel. So it means it's going to push apart, okay, between those two charges over there. So what we're saying over here is, if you have the same type of charge around, they will repel each other. On the other hand, if you bring in the opposite type of charge around, it will attract each other. Okay, so that's the only thing that you have to add on top of the stuff that you have already had before back in the gravitational field and gravitational force. In the gravity, you only have attractive force, but over here you have to determine the sign of the charge first. The opposite sign of charge will attract, same will repel. Okay, cool. All right, so that's additional rules that you just have to add on top. All right, but if it look in like a macroscopic sort of like, think of like the whole material pieces and all this stuff, and if you want to classify by the type of the way that those electrons or those charged particles can travel very easily in that material or not, this might be more familiar to you guys, because this is the way that we classify material around us. That you say, you might have heard of like conductor, like metal. Probably that would be the easiest one. You know that metal conducts electricity. Right? You get electric shocks if you touch on something that have a short circuit and everything, and you have a metal around. So that's why that's indicating that charged particle inside a conductor is very easily moved. Okay. On the other hand, insulator is the opposite one. And you have a question: is human body an insulator? Well, It's sort of like somewhere in between though. All right. It's you have water, you have a lot of water in your body, right? And water actually can conduct electricity a little bit. So that's why, well, it's sort of it's like a bad insulator and a bad conductor, I would say. All right. All right. But anyway, for uh uh normal purposes or stuff, I think our body can still conduct electricity. Yeah, not well, but it's doable. Okay, so insulator will be something that you kind of know that you will be safe. You won't get electrocuted or you won't get electric shock if you know behind this kind of thing like rubber, glass, diamond, wood, and all the stuff. Right, kind of get the feeling. And of course, the one that we use a lot in ship technology is semiconductors. So there is a material that's come in between. When you say come in between means it's sort of, right? It doesn't mean only in between in the sense that it has poor conducting property or poor insulating property, but it turns out you have a way that you can manipulate them. That's the cool thing about these semiconductors. So when you have the way that you can control, so that means you have a way that you can say, hey, I'm going to turn this semiconductor piece into a conductor. Hey, I'm going to turn this into an insulator. So that means you have some sort of like a way that you can adjust the property of this semiconductor. And that starts to get into the logic, right? Because you have a control. So once you have a control, you can say yes and no, one or two. I mean, so it's 0 and 1, you know, turn on and off. So when you start to have that, you have the digital technology, 0 and 1. So when you combine those 0 and 1, that's it. So that is a semiconductor business over there. All right. So that's why your CPU, your chipsets and everything composes of like, you know, semiconductors, pieces combined in like a billion of stuff. It's like in the form of a transistor. And then you have a control, you have a logic, and then it starts to think. And then you can do computational on top of it. Cool. All right. So this is just, you know, just try to link to something around you that's related to the property that rely on charged particle inside. However, for us, we're going to dig deep down into the fundamental of this. We're going to look at single charge one by one first. All right. And on the way toward the end of the course, I'm going to drive you further and further away from this. We're going to start from the building block. What is happening on the charge particle, single charge? When you have a bunch of those charges, what will happen? Learn about the field, learn about the force, and now we're going to combine them, all those techniques and the stuff, and then we'll start to bring in the devices that based on our understanding and we built, you know, in the maybe the first 3 lectures or so. Sounds cool? All right. And toward the end, we can lead you to circuits analysis. That will be very close to real life application. You have, you know, electricity running in your circuits, and then you calculate a couple of things around it. And that will be somewhere toward the end of the course already. Okay. So to get an idea of this one, all right, when you look at this topic, it turns out, I mean, I don't know, have you seen the list in the textbook yet or not? All right, but I started out with the field. And this is, I have to say, maybe this is not a very conventional way of introducing this topic here, because in general, most of the textbook will start with Coulomb's law. The reason that they started out with the Coulomb's law is because Coulomb's law will explain the force between them. And once they have the force calculated, then they introduce the field at the end. So that means the order of introduction of the stuff that I'm showing you right now is kind of like going backward here. It's like we're doing like a tenet. It's like going backward, right? We're going to start from the field, and then I'm going to lead you to the force, and then going to eventually introducing the Coulomb's law. We're going backward here. But anyway, to me, I think this makes more sense. Why we have to understand Coulomb's law first to understand force, and then eventually we're going to introduce the field. When in reality, when I say reality, I mean, well, for physicists' life and all this stuff, they think of the field first, I guess. It seems to me. I don't know, it's maybe only me, but I mean, that's natural. Okay, so what I'm sort of like try to talk to you here is, it seems like if you understand electric field, you understand everything. So it seems like it's a very efficient way of talking about this stuff. All right. So follow me here. All right. So the way that I'm going to do this is this. So with this slide, it looks static and everything because, all right, I'm going to show you how to, calculate electric field right now. And by definition, it's kind of weird because, Ajahn, you haven't talked about force just yet. But it turns out electric field, by definition, is force per unit charge. But then you don't have force yet. So that's why we have to somehow start with the force. So the way the textbook writes down is they must have a test charge. And this is the annoying part for many students over here. They don't get like, why do you need this charge over here? You want to test something and all this stuff. So if you don't like this one, don't worry. Eventually, they are going to disappear. All right. But think for now, just sort of like follow me just a little bit. Let's say you have that Q naught charge sitting there, it's sitting here. Okay. And then you have another charge because there must be some interaction, right? There must be some interaction. So I have the charge sitting right there at the green dot right there. So these two will interact. And because you can see that, Ajahn, okay, let's assume that this is positive. And let's assume for simplicity that this one is also positive. So they are going to repel each other. You guys with me? Each other. They are repelling each other. So that means if you're focusing on the Q naught, so the Q naught will feel the pushing force F pointing away from it. That's a pushing force. But if you pay attention to the Q itself, the Q will experience the same pushing force, but in the opposite direction. This is serious because this one has to follow Newton's third law, the action and reaction. So when the Q is trying to push the Q naught away, the Q naught will actually push the Q away as well. Cool. So everything is still work really well with the Newtonian physics and all this stuff, right? Okay, now it's time because this is the interaction between two charges, right? But I don't want to think about that because if I have to think like this, that means I need two charges all the time. Every time that I have to analyze something about the electricity. So the way that physicists, work around this one is, I don't know if it's called work around or not, but the way that they sort of like imagine in their head is, all right, now is your turn. I'm just going to turn this into 1 Coulomb. You guys with me with this? Every time that I turn my test charge into 1 Coulomb, the force that acting on the 1 Coulomb charge is automatically force per unit charge. Does that make sense?
Okay. Okay. Okay.
Okay, one more time. So first we started out with two charges. One we call test charge. The other one is a charge that's generating things that we are about to call electric fields, right? But the idea is, by definition, the field is the force per unit charge. When you say per unit charge, it means if I set this one to 1 Coulomb, so it means the denominator over here is just number 1. Then the force on that 1 Coulomb charge must be the same magnitude as the electric field. With me? And the idea of having that charge equal to 1 give you the force per 1 Coulomb that eventually give you electric field automatically. By the definition, it's equivalent to you just erase this test charge altogether. Don't need it because you already said it equal to 1, right? So it means it seems like you can imagine that at point P, there's nothing there. And you just have something that we're going to call it electric field. Does that make sense to you or not?
Okay.
Probably not, but I don't get it. What are you doing? All right, what kind of introduction of the electric field is this? All right, don't worry, guys. Think again. Okay, so I'm gonna do this. I don't know if this works for you or not. If I have, all right, a negative charge. Okay, follow me one more time. And what I'm saying over here is you have a negative charge waiting over here. You have a test charge sitting there Okay, it's going to generate a attractive force because now they are opposites in sign. Cool. The Q is negative, Q naught is positive. So you're going to get a attractive force F on the test charge. And don't forget, all right, it's going to have the attractive force on the Q as well, but we are not focusing on that force. We are only focusing on the force acting on our test charge. Now I'm going to set our test charge into 1 Coulomb. Cool. Once I set that one, my force will turn into field because it's a force per Coulomb already. So by doing this is equivalent to I'm just erasing this Q naught charge altogether. I have nothing. I'm just going to call that at this particular point, I have electric field E. Everyone okay with this? Okay, so in conclusion, it's a conclusion number 1 first. If you have positive charge here, and you are at a distance away from point Q, so this means at point P, you will experience an electric field pointing away from the charge originating that field. See, pointing away. Okay. On the other hand, if you have a negatively charged Q, and you are at the distance R away from that at point P, because this is negative charge, you will experience an electric field pointing towards the negative charge Q there. See? So now we have 2 types of charge. One is positive, one is negative. So what you can imagine in your head is positive charge generate the field outward. So what I'm saying over here is if you imagine this, and I try to draw this like, dramatically here. So electric field coming out from this positive charge will point radially outward everywhere. With me, guys? Outward. Okay. On the other hand, for the negative charge particle, electric field will point towards it. Towards. Cool? All right. For those of you that still don't get it, but I don't know what you're talking about. What definition is it? You have already learned how to do this back in the day of Newtonian physics. I don't know you imagine that along with me or not. Okay. So I need some space here. So think about this, guys. I know you have to tip your head a little bit if you want to. All right. But the idea is this. If I say, well, hey, guys, this is Earth. This is me. I am floating here. I will experience the gravitational pull by Earth. Yes. And what is that? Everyone will say, but John, you will feel mg. Yes. And m come from where? Come from me. I have the mass m. The Earth is pulling me in with the force mg, and that is my weight. Yes. But everyone know, if I am not there, everyone will agree with me that at that location before I am there must be gravitational fields waiting for me already there. And that gravitational field right there is going to point down with the value of G. With me here? One more time. All right. So look at the mouse over here. Everyone knows if I let it go, it would drop down to the floor. Why? Because it has the weight. Right now, Earth is pulling this mouse downward, right? Mouse down. However, everyone will agree with me, if I get rid of this mouse, this location right here has already gravitational field by Earth, by our Earth right now, is generating the gravitational pull. waiting for the mass to be located somewhere around here. So once I locate the mass here, this mass will be under the influence of that gravitational field, and it's gonna just flow along with the field down. Does that help? So now you can imagine that our Earth, the whole big chunk, the whole thing can be like a giant ball of this negative charge particle, let's say. So let's say our Earth is like a big ball of electrons, and us is just a positive charge, let's say proton, maybe. Us will feel the gravitational pull down to the floor because now the floor is electrons. We are proton, positive charge. So positive and negative will attract each other. So we will feel attracted to the floor. Okay. How much? It must be the field times the charge. Just like mass times gravity, gravitational acceleration G. And now without us, without protons, you will know, oh, around the Earth here, there must be a downward field waiting. ช่วยไหมเนี่ย Does that help? Okay, if it's not, if this is still not helping, well, I have like some, visualization that help a little bit here. So it seems like now you can imagine that around any positively charged particle, it will have electric field going out. You don't have to have a pair of charges. You only have a single charge. And it just have electric field around it. That's the force field that we're talking about in like Star Wars and other stuff. That's the field. And for a negatively charged, electric field will point towards it. Cool? All right. And now, if you have combination of that, the electric field can go crazy. It can have different shape and all this stuff. So the way that you can visualize this, we call it electric field lines. And it works so well on the textbook or on a paper because you can just draw lines on there. But in reality, it has something, more complicated stuff because the strength of the field, just like gravitational fields, everyone knows if you go far away from our Earth, the gravitational pull from the Earth will die down. It will get smaller and smaller the further away that you go from our Earth surfaces and all this stuff, right? So that means there must be a distance related to where you are relative to that source of the field. So to better represent this one, please, I will put a link on this one. We need some simulation here, and that will help a lot. So you guys can try this if you want, and I can go there as well. Here we go. All right, so you have that link that I'm going to get there as well, and see if I can get there. Chat. Here we go. All right. So once again, this is the Colorado simulation in physics. All right, and this one is in the topic of the charge and fields. Here we go. This is a cool one that you can play around. So look at this one. I just checked that show electric field, right? And in the future, we'll come back to this simulation because it's a very good visualization tools over here. Now I'm just going to drag one positive charge there. Do you see this? Okay, let me put it in a good position there. See? So because I place a positive charge there, electric field around it is going to point outward. But then you can see that there is the intensity. Yeah, the intensity are also changing. So this is kind of nice because if you look at the brightness of those arrows, it will give you a sense of the strength of the electric field, which makes sense. If you go further away from this chart, the electric field strength should be lower and lower. Cool. All right, but you have an option to just don't forget about that. Just care about direction only if you want to. So this is a better representation in the sense that this one, we call it a vector field, not only like electric field line, because line, it just doesn't have any information about the intensity. So what you have over here is a vector field. So for those of you that already taken calculus 4, will sort of understand what does the vector fields mean. Is the field of vector quantities. All right. So let's try again. I can reset. I can place the negatively charged particle here instead. and it will generate electric field pointing towards this negatively charged particle around. Cool. And now you can go crazy if you want. See, you can now have a system of charges you can play around. And of course, we will have to do this. We have to analyze like, okay, what will be the electric field at particular point? All right. But the idea is very simple in the sense that if you come here from a single charge, all right, the good thing about this one is you have a sensor. You can place a sensor there. See, and then if you move sensor around, this will see like, hey, if you close, electric field will be very strong. And if you go further away, electric field will be smaller and smaller and smaller and smaller. Is that cool? Right, it's getting smaller. And the way that we can describe that, we need an equation, right? So you will get the relationship between the parameters that needed to calculate the strength of the electric field at a point. But the idea is, if you have more than one, you just have to combine those stuff. You have to combine electric field from those charges, and it's going to be just the summation of all the electric field vectors. So that's why we need just to know how to do the vector summation one more time. But the basic is simple. You start very easily from knowing that electric field from positively charged particle pointing outward. Electric field from negatively charged particle will point inwards toward the source. Cool? All right.
Okay.
So with that, now we can switch back. I don't know if this multiple ways of describing the field is helping or not, but I hope the analogy with the gravitational acceleration G seems to help, I think, because you're already familiar with that a lot. All right. So the idea is to find the net electric fields at any point. You just need to do the vector sum of all those electric fields. Okay. For example, so let me show you this over here. If I place one positive charge on the left, one on the right, what I'm doing over here is this. Well, Ajahn, if I want to figure out what is the electric field at this point, my black dots over there, and as you can see, the electric field lines already curved down. So you can think of like, oh, electric field over here is supposed to point in this direction. But to prove or to verify that, this is how it works. Guys, start from the left positive charge. Electric field from the positive charge particle will go like this. So I just draw a line of sight over here. So the electric field from positive charge will point outward. You guys with me? Let me call E positive vector. Okay. Now you do the same thing with the negatively charged particle over here. But we already agree that electric field from negatively charged particle will point towards it. So it's going to point towards it here. Let me call this E negative vector. Now, what do you need is just finding the net, which is the vector sum of these two vectors. But now you can see, oh, that is a mirror image, right? So what I can do is, okay, I can break this into two components. And I can break the blue into two components as well. And now the one that is pointing up and the one that is pointing down is going to cancel each other out. See that? So that's why you get the net electric field at that point to be pointing toward your right side. And that's the reason why electric field at this point is going to point in the horizontal direction right there. That's the net sigma E right there. And you are done pretty much.
Okay.
Cool. All right. That's the whole thing. You're going to be able to figure out a lot of stuff like this. Okay. So what is the electric field at point A, B, and C? No problem. All you need to do is just figure out the electric field from each individual charge. And you just sum all those contributions from each charge, right? Not hard. It's quite easy, right? I'll show you with examples right there. But the way is, don't be afraid to apply a simple calculation there. It's just, you do it one at a time. So you start from, hey, what is the electric field from the charge number 1? What is the electric field from charge number 2? What is the electric field from charge number 3? Using a very basic agreement. Positive charge emits mean radiate electric field out. Negatively charged have electric field point towards it. That's it. Okay. Now the way to calculate that though, this is the formula for you. And this is probably the only formula that you need right here. Look at this. It's some constant right here. All right. We're going to talk more about this constant, but for now, let's call it like a It's a Coulomb constant. And over here, this is a charge that generate the field in the unit of Coulomb right there. That's a charge. The R over here is just the distance. So this is in a meter square. Okay. So from the look of this, it's like, it looks very close to like the G M over R square back in the gravitational fields. And that's exactly right. That is amazing that it turns out the law that describing the electric field strength have the same function just like gravitational fields. So that's why physicists just dream of like there must be like a grand unified theory that describes all the forces in the universe and all this stuff. It's by accident, I don't know. But it's 1 over R square function, just like gravity. All right. So this is what it is. So this is the way that you calculate electric field. At a distance R away from the charge Q, it's a KQ over R square. That's it. So for example, right here, what is the electric field at point P? You say the magnitude of the electric field is KQ over R square. And that's it, you're done. Cool?
Okay.
The only thing that's complicated is the vector. And because it's points in the radial direction, this is the annoying part. Electric field just radiate out. So that's why you got a magnitude over here. You just have to have a way to say it's pointing in the radial outward, right? It's a radial outward. It's radial and it's outward. So we have this R hat notation for it. So R hat is this dude right here. It's just saying that, hey, is a radial direction. When I say radial direction, it means everything over here that you see is all R hat. R hat. R hat. Isn't that weird? This is a weird. And people don't like this one a lot because, well, Ajahn, how can a vector point in all directions? But too bad. That's what it is. This is a different kind of coordinate than the X, Y, and Z coordinates that you're familiar the most. Okay? So if I want to compare this one to the one that you're familiar with is the X, Y, Z. And then the X, Y, Z cases, what you have over there is you have the I hat, J hat, and K hat. You remember that one?
Okay.
Okay. The reason that this one looks very counterintuitive because in the I, J, K hat, they are pointing in the same direction. It's the unidirectional units vector. I is always point along the positive X direction. J always point in the positive Y. K always point in the a positive Z. But for the radial, the R hat, it's point in the radial direction. So this radial is point everywhere. I don't even know how to call this every direction. It's not even 360. It's like, it's not even 720. And you have to say like, it's like 4 pi steradian or whatever, right? So it's a spherical radial direction. So this is, we are sort of like creeping in, sort of like, you know, jump into a different coordinate system. We are trying to use spherical coordinate system, not Cartesian XYZ coordinate system anymore. All right. I know I'm throwing a bunch of terminology to you guys right now, but all right. I hope things will get more natural more and more we do the exercises. All right. But for now, I just want to talk about this because when you read the textbook, this is annoying.
Okay.
That's R hat. That is sort of like attached to this equation is annoying. So for those of you that still feel annoyed with this, you can sort of right now take this one for now, guys. Just take the magnitude. You will feel much better. All right. Just say, okay, Ajahn, I'll take the magnitude first. And then I just know in my head that if it's positive, it's going to point outward from the source. And if it's a negative charge, it's going to point inward. That's it. It seems to be easier. And don't worry about the notation of the R hat at the moment. Cool. Alrighty. All right, guys. So I think, I don't know, this is the longest introduction to this. But I hope it helps in the sense that back in the day, I just take like maybe like 10, 15 minutes talking about this one and then just jump right into the exercise and everything. But it seems like majority of students that haven't taken any electricity and magnetism before seems to get lost because like this is the first time seeing this. I don't have any, clue what are you talking about. So I hope by sort of like give you the connections with gravitational fields, okay, think of the G, and then this is the business that you're trying to do with the charge. And now I'm trying to say that the charge taking the role of the mass back in the day of the gravity. So it seems like you have a better starting point. So the mass generate the attractive fields around the mass all the time. And that fields generated by those masses are just the G that we are familiar with. If we are on the Earth right now, it's like 9.8 meter per second square. That is going to be exactly the same as the charge. If the charge is negative, it will generate an inward field, just like the G, exactly, okay? But then we're going to call those electric fields, not the gravitational fields anymore, because it came from charged particle. I don't know, does it help a bit? Okay, all right. Anyway, guys, I think let's take a break first, shall we? All right, and then we'll come back and we attack a couple of examples. I think you're gonna have a lot of fun. All right, and once we get to these examples, then you will know how to calculate electric fields from system of charged particle, and you will feel much better after a few examples over here. All right, guys, so take a break right now.
Okay.
And I'll see you guys 11. Sounds good? All right, guys, take 10. All right, guys, so let's dive into calculation, shall we? All right, so you have three equal positive charges, Q, are at corners, the corners of a equilateral triangle of side A as shown. What are the magnitude and direction of the electric field at P, the top of that triangle there, due to the two charges at the base?
Okay.
All right, what do you think? So you sort of like get an idea what kind of question it's going to be, right, for the electric field. All right, and I purposely put this exercise to be the first exercise to try because that's what we have been discussing about. It's just like, okay, we have both force and field in our discussion before, and we have to talk about a pair of charges every time that we talk about the force. And if you only need to talk about a single charge at a time, you can only talk about the electric field. All right, but this one, you have a setup that you already have everything, but they just only ask you to figure out the electric field at point P. See that? So if this is the case, my point is you can just ignore this Q at the top. I don't care because I have no business of dealing with this at this point. So don't worry about that one right at all. Let's say right now, don't worry about it. Okay, and just say what is the electric field at point P due to those two charges at the base. Okay, so let's do it one at a time, shall we? So first thing first, you look at the left charge. This positive charge on the left will generate electric field everywhere outward because it's a positive charge. With me? All right, but we only care about what is going on at point P. So at point P, you can pretty much draw this. It's going to electric field is going to point in that direction. Okay. So that means at point P, you're going to say, hey, that electric field is going to point there. Let me call this E1 vector. Cool. Same thing will happen to the electric field due to the charge on the right. So on the charge on the right, electric field will point out because this is a positive charge particle. It's going to point out all directions. Cool. But of course, once again, we only care about what is going on at point P. So at point P, you will say you're going to get electric field point in, okay, I think instead of writing a line, I'm just here drawing a dash line. It's going to point in the radial direction like that. Cool. All right. And because it's a positive charge, eventually it's going to point outward. So it's going to point out in this direction. It's too thin. There you go. Cool. And that's it. At point P, you only have contributions from those two electric field vectors. I can call this electric field vector from the right to be E2. All right, now, what are the magnitude of E1 and E2? So let's start from E1. So I'm going to call here magnitude of this vector, or sometimes you can just say E1 without the arrowhead on top. That will mean you only care about the magnitude of this vector. It's followed from that formula, the K times the charge generating the field, which is Q, over the distance from the charge to the location of calculation, which is A square. So now you get the magnitude, and direction is along that red arrow right there. All right, you don't even have to write it, but at least it say, hey, that is pointed in that direction. All right. Well, for us, I think if you write down like this in your paper, I think I can get it. All right, I kind of, okay, I got it. All right, so E2 magnitude, or you can write just E2 like this, that's fine. K, charge generating the field, which is just a Q, divided by the distance from that charge to the location of calculation, which is A again, and it's going to point in that direction. Cool. All right, so now you both, you have direction and magnitude for each electric field. So now it's time for you to combine those. Just combine them, just like you have two vectors, you want to add them. So what you do is you can use like a parallelogram if you like. You know that at the end, you're going to get this net electric field. Let me call this a sigma E. Cool. Or you can just do the breaking the electric field into two components. E1 will you get like a horizontal component and the vertical component. Take that one out. So this is the E1, or if you want to call this theta, it's going to be E1 cosine theta and the E1 sine theta. Do the same thing for the green. You split this into two components, vertical and horizontal. The horizontal 2E cosine theta, which is going to be the same theta there. And you have E2 sine theta pointing on top. Is that nice? All right. And you can see right away that the horizontal components will eventually cancel out. Why? Because look at this. The magnitude of these two vectors are exactly the same size. Cool. That's no problem.
Okay.
So you only have just the vertical components left pointing up. So what you can say, the net electric field magnitude, right? I don't have the arrow sign on top. It's just going to be E1 sine theta plus E2 sine theta. Here we go. All right. And it's pointing up. So for some of you, if you want to do it in one line over here, you can write here, head, like that. And you can say point up. Up could be like J hats if you want. You guys with me with this? All right, but it's your choice. You don't have to do a vector format right now. You can just calculate just the magnitude because, we just want to sum these two vectors that is pointing up together first. So it's going to be KQ over A square sine theta plus KQ over A square sine, just two of them, let's say. It's a 2KQ over A square. But now the sine theta is not too bad because the theta is just the angle that you just created right there. All right. So if this is theta, what you have over here is this is your theta as well. So you can define your angle whatever you like. You can, if you can use the other angle if you want, that's up to you. There's no big deal. But the idea is you will be able to figure out this theta very easily. All right. So the base over here is A over 2. This, you can use Pythagorean theorem over here. That is going to be A squared minus A squared over 4 under square roots, on and on. All right. But anyway, the point is you will be able to figure out the sine theta. That's what you have. Or, for this particular problem, it's a equilateral triangle. So all you need to know is just this whole thing is 60 degrees. All right. But that's the whole point. The point is you just use geometry to figure out what kind of angle that you use in your decomposition of the vectors, and you just add them together. All right. So over here, you just say it's a 2 sine 60. And that's it. Root 3 KQ over A square. That is your net electric field. And of course, you want to put it in the vector format. You can just say, hey, and then you can say up. You are done.
Okay.
All right. When I say up like that, to make it a little bit cooler, You can use J hat if you want. Or you can just say up. Whatever, that's fine. All right. So it depends on how familiar with the vector notation you are. If not, man, just describe it. It's not that hurts. I mean, it's fine. You have both magnitude and directions. You already complete the components that you need to build a vector, which is perfect. Cool. See, not too bad. All right, try again. And if you feel comfortable with this, then I mean, the rest of the electric field calculation is not that bad. All right, try again, guys. Figure shows two charged particles on an x-axis. One now is negative. All right, so it's negative q. The value is given. The other one is positive, same size, but opposite sign of charge. And the distance is given at x equal to 3 meters. So that means you already know that this one is a 3 meter long, 3 meter long. On both of them, what are the magnitude and direction of the net electric fields produced at point P, which is 4 meters away from the origin. So you know this is 4 meters. All right, you want to give it a shot? Yeah? Woo. All right, this might be annoying, right? All right, but once again, the question goes exactly the same as the previous one, but now it's less confusing in the sense that you are asked to figure out the electric field directly, right? There's no, intervening from the other charge on and on. All right, so go ahead. What should it be? Well done. Let's start from the negative Q on the left. So what you have here is, I can just draw the line here. Because it's negatively charged, at point P, the electric field will be generated, right? Pointing towards that source. So that means the electric field from that negative Q will point, okay, it's too thin, sorry. There you go. There you go. Electric field will point down here. Nice. All right, now look at the positive Q on the right. Okay, so once again, I just draw the line aside here. There you go. Now it's positive Q. So electric field will point away from it. So electric field will point out there. But once again, from the symmetry, and you sort of like now the formula to use is KQ over R squared. Q are the same, right? Same Q, it's just opposite sign. R, the distance are also the same as well. And you can see that it's supposed to be 5. It's a 3, 4, and 5. So from Pythagorean theorem, you know that side is going to be 5. So let me call this E negative then. And let me call the green arrow to be E positive then, all right? Okay, so you use the same trick because the idea is you just want to have the combined electric field. So what is the net electric field? It's just going to be the summation of those two in the vector format, of course. There you go. And what you do is you break this into two components again. Okay, and then you can define, theta, whatever you want. This is going to be theta if you like that. Okay, so the component that pointing up is going to be E positive cosine theta. The one that's pointing down is going to be E positive sine theta. Same thing that happens with the red vector. You break it into two components as well. Okay, and that we're going to be E negative. And you just use the same theta right there, over there. So it's going to be sine theta over here. And the one that's pointing down is going to be a negative cosine theta. Cool. All right. And once again, the vertical component will cancel each other out. So nothing, no vertical components. You only have left with just the horizontal components pointing to your left. So your net electric field is going to be equal to E negative sine theta plus E positive sine theta. And now you can say it's pointing to your left. Or you can use a negative I hat if you like. Cool? All right. So when I say this X is pointing in the negative X direction, so I use a negative I hat to specify the direction there. And once again, the E negative and E positive, oh, it's supposed to be negative here, guys. Sorry, not E1. Negative. Okay. And the magnitude of the E negative is going to be the same as a E positive, and it's going to be KQ over 5 squared. You guys with me? Okay.
Okay.
All right. I just plug it there. In there, it's both KQ over 5. So I get 2 KQ over 25. And then the sine theta is just 3 over 5. It's opposite over hypotenuse over there. So it's 3 over 5. And it's point in the negative x direction. So I put a negative I hat over there. And at the end, I can substitute the value. All right. I haven't talked about the value of the K just yet, but I just want to leave it there. So it's 2K. Now you plug in the charge. Just take the magnitude to 3.2 times 10 to the negative 19 Coulomb times 3 over 5 divided by 25 negative I hat, and you are done.
Okay.
Wrong sound effect. Yeah. All right. So the K value, actually, you can look it up. It's about, this one is about 9 times 10 to the 9. Okay, the unit is going to be just inverse of everything. So it's going to be, you can say it's going to be Newton per Coulomb meter square. Okay, Newton meter square per Coulomb. If you like. There you go. All right, but anyway, it's a constant. The reason that I don't want to focus too much on that K yet, because we will have a chance to talk more about the constants that involved in some other stuff that has different form as well. So I will introduce the numerical value then, okay? So how to know if the value of Q is positive or negative? Okay, very good. So usually it will be given because this is a system of charged particles. So usually it will be defined like, hey, it's here, it's negative charge, here is positive charge. However, when you want to utilize this formula, E equal to KQ over R squared, if you notice, I think this is a very good question. I think you are wondering about this. This Q over here, you do not need the sign at all. Does that make sense?
Okay.
If you notice these two exercises that I just did, when I was calculating the magnitude of the E, I don't care, is it positive or negative? Because the negative and positive charge will just only be used to determine the direction of the electric field vector. Make sense?
Okay.
All right. And the sign, and the value, the magnitude of the charge will give you the magnitude of the electric field. And the positive and the negative sign give you the direction. Is it the field supposed to point away from that? Or if it's negative, is it supposed to point towards it? That's what it is. Very cool. All right. Thanks for the question. It's very good. All right. I think you, from these two, you get a sense of what is happening. Okay. So come back here a little bit. For those of you that's kind of like, okay, sort of like, I get the idea. And if you remember this one, I erased the charge on the top of that triangle out, right? But I think you start to see the connections. If I want to bring back, if I want to bring back that charge, now you start to see the scenario that I was just said before the break. This is exactly what we had in the gravitational field, right? So that means right then, what you have over here is just like, okay, Ajahn, I don't have the charge at that point just yet, but there is electric field waiting for me. And if I place a charge right there, this charge will experience the electric force. There you go, guys.
Okay.
All right. So this one is just like give you a hint of what is about to happen in terms of the connection between the force and the field. It's that simple. So that means once you have already calculated the field, I mean, you already know what is supposed to going on if you were to place a charge there. You're going to get a force, just like you already had a place or location with the G, gravitational acceleration. You know right away, if you put the mass there, it will have the weight of mg, and your life is done.
Okay.
I mean, your life is done. Your life in physics is no need to worry anymore. Yeah. All right. So that's what I was hoping for, that by understanding the field first, knowing the field will lead you to knowing the force automatically. It's just a matter of placing a charge there under the field, you get the force. Yeah, It's like buy one, get one free or something like that. Yeah. All right, guys. So move on, try again. All right, let's do something that's sort of like free floating system. Don't have any X, don't have any Y, but just, some system floating around. So, I mean, floating doesn't mean like it's moving, but I mean, it doesn't have any orientation in the XY formats here. So in the figure, the four particles are fixed in place and are charges, all right? Q1, Q2, Q3, Q4, given the value. The E over there, don't forget, that is just a constant. It's just a charge of a single electron, okay? It has a definite value of 1.6 times 10 to the negative 19 Coulomb, on and on. But we just use E for that. So that was still this E right there. Use here, all right? So E is this numbers right here, right? It's just easier to write E than just those listed of number, number, the long number there. Okay, all right, so over here you have Q1, Q2, Q3, Q4 arranged as shown in the figure. So the distance is also given to be 5 micron. What is the magnitude of the net electric field at point P? All right, you want to give it a shot? The idea is going to be quite all right in the sense that, right, even though it's not lying on the XY coordinates or anything, but the concept stays the same. So let's sort of like go through this one by one, shall we? All right, start from the Q1. All right. So, I mean, for those of you that sound like still want to think the way that I was saying is just like around Q1, you have electric field already generated around. Same thing with the Q2, Q3, and Q4. They're all having electric field around it. Crazy, right? Every charged particle will have its own electric field. All right. Q1, Q2, Q3 are positive. So electric field is pointing outward. This is like look really bad over here. And then Q4 is negative charge is going to point inward. Right. So I intentionally try to write this thing like make it look messy over here. Just want to depict that this is actually is already there based on the electric field concepts. Right. Don't forget this is just a theory. Right. In reality, they might not have this around any charged particle, right? But this is the way that we can deal with this. So we assume that all of the charges over here already have electric fields around, okay? But what we care about is what is going on at point P, correct? So that's what we want to do, all right? So let's get rid of all this stuff, and we just want to focus on what is going on at point P. So at P, start from Q1. So Q1 is positive. So it's, okay, let me draw a line aside here. So you're going to get a vector coming from this pointing outward because it's positive. With me? All right. And I can name this E1. No problem. Okay, it's pointing down. Now let's look at the Q2. So the Q2 is also positive. So at point P, so what I can do, once again, let me draw a line aside there. So electric field due to Q2 will point outward as well. It's going to point up like this. And I can name this E2. But now you start to see, but John, wait a second. Q1 and Q2 are having the same magnitude. Plus, they are separated from the point P with the equal distance, 5 micron. So now you know right away the magnitude of E1 and E2 must be the same by symmetry or by formula, KQ over D squared. You guys with me?
Okay.
So definitely what you can conclude right away is, you don't need to calculate anything here. These two will automatically cancel each other. Nice. All right, save a lot of time. Okay, by symmetry. Cool. Now let's look at Q3. Q3 is still positive with 3E. So when it's positive, mean electric field will point away from it. There you go. Oh, it's too thin again. All right. Let me write a little bit bigger because now the Q3 is kind of like strong. It's the charge is 3e. Okay. And then now you have Q4, which is negative 12e. Whoa, it's even bigger. But the point is negative. So it means it's going to point towards it. You guys with me here? Q4 is negative. So it's going to have an inward, point towards it, electric field. All right, now let's calculate the magnitude, shall we? So magnitude of Q3 field, let me call it E3, is going to be, all right, I don't put the arrow or on top, so that is the magnitude already. It's the K times the Q3 divided by the distance, which is D square. So it's a K, Q3 is 3E. See, I don't care about the sign, divided by D square. Just leave it there. That is the magnitude of the electric field number 3. And move on to the electric field magnitude of the E4. So let me call this E4, electric field from the charge number 4. So that will be K Q4. Now the distance is 2D. See, the distance from the charge Q4 to the location of the calculation is 2D. So I just put 2D here and square. Nice. So what you have is going to be K. Now it's 12E. I don't have to care about the negative sign. Divided by 4D squared. And this cancels to be 3. So what you can see is, once again, the magnitude of the E3 and E4 vectors are exactly the same. So they will cancel each other. So conclusion of this one is the net electric field at point P is 0.
Okay.
You're done. All right, isn't that cool? So that's what it is. So that's why I'm saying that the process of calculating this one is very straightforward. You just consider electric field one by one. Yeah, just going like, what is the Q1 generating? What is Q2 is generating? Q3 generating? Q4 generating at the point of interest. And once you have all the vector that contribute to the net electric field analyzed and everything, just sum them up in the vector format. Just do the vector summation and you are done.
Okay.
Cool. All right. And I can add on top of this very easily if I accidentally place a charge right there. Think about it. But Ajahn, let's say if I place Q5 at that location, what will be the force on it? There will be no force because the field is 0. It's just like you don't have any influence from the field at all. So you are like, floating around in space or something in the context of gravitational field. Same thing. So it means you can place the Q5 charge in there, the net force will be 0. Cool. All right, that's an idea. All right, so that means, so once we already learned about the electric field, so I think there are some sort of like the characteristic of electric field that you can draw from those understanding very easily, just for fun. All right, let's see if you agree with this. The direction of the electric field, in the case that you use electric field line to represent your field, will be in the tangential direction, which is fine. It seems okay, because if you go back and look at the electric field line here, and if you want to know, hey, Dan, what is the electric field line here? It's going to point in the tangential direction there. That's what it is. That's natural. So when I say natural, means when you try to draw lines connecting the field, you try to draw lines that is tangential to those vectors already, right? So it's just going forward and backward, right? So that's the way that you draw the electric field lines anyway. Part B, for B, it's kind of makes sense when the field is strong. It seems like the density is gonna be high. So that means the location that the electric fields lines are dense, that will represent the strong electric field as well. That's kind of makes sense, right? Because if you go back here, just a simple figure for our electric field from a single charge. Everything is going radially outward, right? So if you look at the location that is very close to the electric, close to the source, the number of lines per unit area is high. But now if you move away from it with the same amount of area, see, the lines are going to be less dense. Make sense? So it seems like there is a connection between the density of lines and the electric field strength. That makes sense, because the closer that you get to the charge, the stronger the field, you know, from the equation KQ over R square. But when you draw a visualization using the electric field lines, okay, the closer you get more lines per unit area. So higher density of lines mean stronger. So this is high E, and this is going to be low E. Okay, that makes sense. All right, part C. All right, this makes sense that the field starts on positive and ends on negative. That's what we base this one on, because we said electric field irradiates out, irradiates, sort of like diverge from the positive charge and converge into a negative charge. So you can think of it like the line starts from positive charge and ends on negative charge. That seems to make perfect sense. Okay. And D, you will never see a crossing between those electric field lines, because that's bad. We never have this because you always do the vector summation. So when you do the vector summation, you never have the decision to make. Does that make sense here? Because if you have any intersection, or I mean, you know, some sort of like the crossroad between one line and the other, the question is, what will you do? Are you going to point in which direction, make decision? Or no, there's no way, right? So electric field lines do not cross, okay? You only have line that go single lines all the way, because it came from the net electric fields calculation already. This one, it's like unfinished business somehow. Like, why don't you just add these two vectors together and call it some value? All right. So does that make sense? All right. So this seems natural, right? But you don't have to worry about this much, because there will be no question about asking you to, hey, draw the lines or anything, because we just do a pure calculation. Okay. All right. So with that, I think we can draw to the conclusion of Ajahn. You just said that if you know the field, you know the force. But yeah, because you see, the concept looks exactly just like mg. Does that make sense to you now? That's mq, sorry. Does that make sense now? So if you know how to calculate fields, you place the charge in that field, you can get the force simply by charge multiplied by the field. Because we define the field to be force per unit charge. Right? So if you want to get back to the force, you just take the charge multiplied by the field, you get the force. But I mean, my point is, it looked exactly just like what we had back in the mg day. Mass, take the rho of the charge. G, take the rho of the electric field. Mg is the weight. The weight is just the gravitational pull. QE is going to be the electric force due to the electric field. Cool? All right, so with that, so you can pretty much imagine this. And actually this one supposed to being used in a real application before in the old display technology back in the day of the cathode ray tube. I don't know, I think you already, I think you haven't seen one. I don't know. But anyway, the TV that used to be like a super big box, you know, super fat and deep and everything. And it used the electron gun to shoot electron and hit the surface that has like a phosphor that, you know, give you a brightness and all this stuff, and to have a pixel display by hitting that pixel with the electron guns and all this stuff. And the way that you can control the direction of the electron to hit each pixel is by using electric field control like this. All right, but we don't use that anymore, of course. So what you have over here is, you can imagine this. If you have a way that you can generate electric fields in a uniform manner like this, electric field is pointing up, 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 and then you shoot an electron horizontally. So if I want to ask, hey, what kind of movement of this electron under these electric fields? Everyone will feel, Ajahn, this looks very familiar. I think we're going to get a projectile motion. Does that make sense?
Okay.
Why? Because at any point in time, you have an electric field. So that electron will feel the electric force. Okay, follow me here. Electric field is pointing up. This is electric field, right? But according to the equation, force equal to QE, yes? But the electron has a negative sign, so that's perfect. So when it has a negative sign, mean it's going to be negative E times electric field. So the negative sign that comes in the front will say whatever the field is pointing to, the force will pointing in the opposite direction. So that means these electrons will experience the force pointing down, equal to negative E times electric field. Does that make sense?
Okay.
But then, as you can see, no matter where these electrons is going to be, that force, which is negative E times capital E vector here, stays the same. So this one is the same thing as you throwing a ball horizontally under gravitational acceleration. So that's why you can say, hey, I can use the techniques that I did with the projectile motion and calculate the trajectory of these electrons perfectly. All right, but we don't do that.
Okay.
Just give you an idea that the similarity between the gravitational pull and the electric field pull are exactly the same, right? You can pretty much compare and contrast and make analogies between the two very easily. Cool. All right, move on. So I hope you get the whole package by just learning how to calculate electric fields. So here we go, guys. So we can now wrap the Coulomb's law by saying that. All right, so stick with me here, guys. Almost done. I have a charge Q1. Okay. At a distance r away from this charge, I have another charge Q2. My question now is, what is the force on Q2? Here, force on Q2 due to the Q1. Okay, the way that I am going to show you is, this is what we did today. First, Jan, don't put Q2 here just yet. Just say, what is the electric field at point P first? Okay, follow me here. So electric field at point P is going to be K Q1 over R squared. You guys with me? Once you're done with that, I'm just going to place Q2 right here on top of this. So what is going to be the force on Q2? It's going to be the charge, which is Q2 that I just placed, times E at point P. You guys with me now? Force is the charge times the field. Charge is Q2. Field, we just calculated, is E sub P. So at the end, what you get is K Q1 Q2 over R squared. And that's it. It is this equation right here.
Okay.
And that is our Coulomb's law. So Coulomb's law is the equation that is trying to tell you what is the force between a pair of charges. You can do equally well with what is going on Q1. So if you want to calculate what is going on with the Q1, you want to, hey, Bajan, I want to know what is this force in blue over here. What you can do is you can ignore Q1 for now. And let's say, well, hey, Dan, I want to calculate the electric field at point O, then say, let's say that's my point O. So the electric field at point O is going to be K Q2, because that's the Q2 that is generating the field right now, over the separation R squared. And now once I have that, I bring back that Q1. What is the force on Q1? So the force on Q1, which is the blue force over here, is Q1 times E at point O. Does that make sense?
Okay.
Charge times the field. And what you have? K Q1 Q2 over R squared. Exactly the same.
Okay.
And it has to be, the form of the force between two charges must be following Newton's third law, action and reaction. Why not? See, because the equation, because look at the equation, they look exactly the same. It's symmetric, Q1 and Q2, but of course, it's going to point in the opposite direction and it's acting on a different charge. But in terms of the magnitude, it must be the same because action must be equal to reaction. And this is Coulomb's law, guys. Yeah.
Okay.
And now I think it's time that we can mention about the K properly. So the K over here is called Coulomb Constant, and it has the value of this, which is, all right, usually we approximate to be 9 times 10 to the 9, make it easier for us to imagine and everything. And this line right here, just wait for it. Okay, don't worry about this now, but we're going to have a chance to dig a little bit deeper into this. But John, there is another constant, all right, and this constant will pop up later. But in some textbook, they just stated right away that actually K is 1 over 4 pi epsilon naught, which it's just another constant. So don't worry about it. But there will be some story behind this, and we're going to deal with that maybe a week from now. Okay. So in conclusion, Coulomb's law is inverse square law. No problem. Okay. Depends on the magnitude of the charges, Q1, Q2, no problem. Okay. And the rest is up to you to determines the direction of the force. If Q1 and Q2 are the same kind of charge, it's going to be a repulsive force. If Q1 and Q2 are opposites in charge, they're going to be an attractive force. That's you to determine. So this equation is good in the sense that this is a magnitude. Make it sort of like, okay, you separate into two tasks. Think of it that way. One is determine the magnitude, and the other one is determine the direction. Once you combine those two, you get vector. And we are good.
Okay.
Woo. Not bad, I hope. All right, guys. So this slide just showcase one more time. I already did on the previous slide saying that, hey, Coulomb's law is following Newton's third law, action equal to reaction. And the force acting on one must be the same as the force being acted on from the other, right? It has to be, okay? And if you have more than one force acting on a single charge, the net force is just a vector summation one more time. It's nothing different. You can now do the net electric field calculation, or you want to do net electric force calculation. They are the same thing. Well, not exactly the same, but they are closely related simply by having the charge at the location of the field or not.
Okay.
Cool. All right, guys. So let's do this one as a last exercise of the day. Sounds like fun. All right. And I think we can leave the rest for like a practice or a review for next time. Oh, actually, why don't we stop here? The reason is because, all right, I got it. We're going to have exam on Sunday, which is not related to this at all. So I think we can just give you an idea like, hey, all right, I think we already accomplished a lot. We already learned how to calculate the electric field. Keep it there. Study for the second exam. And then we can attack these problems after the second exam. Sounds like better plan there, okay? Because I think maybe I was already too much. I mean, to put everything here. What will be in the final? Yeah, this is going to be in the final, the electricity, yeah. Oh, second will be waves and oscillations, oscillation and waves, yes. Yeah, oscillations and waves, yeah. Module number 2, okay. Should we look in the lesson 13? Oh, okay. Oh, you don't have that? Okay, let me check on the video. But in terms of the material that is going to cover, it will be up to video number 14. Yes. Yes, correct. All right, I'll put another copy of the video for section 1 as well to make sure that both sections have the same amount of video. Yeah. So what's the handout material in the second? Okay, if all right, let me clarify that so you guys won't get confused. So let me make sure that I quote the material properly. Okay, so in terms of the handout, it will be handout 4 to 6. Is it good? There you go. All right, that will be clear. All right, guys. So that will be for sure. So exam 2, handout 4 to 6. That's it. That's clear. Very nice. Okay. And all right, if you want to talk about the homework will be 5 to 7. Oh, is that, do I have 8 for that? No, just 7. Okay, 7 is good. All right, very good. So in terms of the homework set, is going to be homework set 5, 6, and 7. So homework will be 5, 6, 7. Okay, that's good. Homework will be 5 to 7. Yes. Okay. All right. So once again, oscillation and waves. That's it. All right. That's our exam number 2. I hope this is clear. And then I will put this information on our Google Classroom page as well, just to make sure that everyone do not study too much. All right, guys. So that's it for today. Sounds good? Any further questions? All right. If not, then okay, guys, take care. And yeah. Oh, okay. And lecture video number 14. Yes. All right. And video up to lecture 14. There you go. Perfect. That's it. Very good. And I will make sure that both sections have the same amount of video because I sort of like reduce some of the other sections. So once or twice. Yes. All right. So I'll make sure that the material is up in the Google Classroom properly. Okay. Very cool. All right, guys. So if not, then I will have the Saturday at noon to 2 if you want for Q&A. If you have any last minute question before the exam, still open for that. Or if you want to join in the early sessions, that is fine too, 10 to 12. All right. So overall, all in all, it means that I'm going to be pretty much available from 10 a.m. to 2 p.m. on Saturday. Yeah. Just for the second exam Q&A. All right, guys. All right, so that is it. And there will be no further material for you to study at this point. Make sure that you go back and study the module number 2. Yeah. All right. Yeah. And then for the exam number 1, as I said, it's come down to while you were doing the exam number 2, I will be grading the exam number 1. So I think by the end of that night, then once you submit your second exam, I will submit your exam 1 score. Yeah, I think that will be the timeline there. Okay, very cool. All right, guys. So I hope that's answered a lot of your question and concerns. All right, guys, take care, and I'll see you guys on Sunday. All right, if not, then I'll see you on, maybe you're not seeing me, but you'll see my exam paper on Sunday at noon. Okay, guys, take care. Bye-bye.